Hello everyone and welcome back to the next lecture of control systems. In this presentation we are going to discuss transfer function of a closed loop system. So let's get started. The transfer function that we have discussed in the previous lectures was defined for an open loop system. If we consider an open loop system having gain Gs, the reference input Rs and the controlled output Cs, then we can write Cs is equal to Rs multiplied with Gs, because we all know the output is the multiplication of these two functions. So if I transpose Rs to the left hand side, then we will get the Laplace transform of output to the Laplace transform of input, which is the transfer function of the system Gs. But this transfer function is defined for an open loop system. Now, if we consider a closed loop system, then we have this closed loop system in which the reference input is Rs, Gs is now the forward path transfer function, Cs is the controlled output, and this is the feedback element. And we know that the feedback element is the differentiating factor between a closed loop system and an open loop system. There are two types of feedback in case of a closed loop system. The first one is the positive feedback, in which the feedback signal is in phase with the reference input, and the other one is the negative feedback, in which the feedback signal is 180 degrees out of phase with respect to the input signal. The positive feedback is represented with a positive sign and the negative feedback is represented with a negative sign. So now we know that there are two types of feedback in a closed loop system. The first one is the positive feedback and the second one is the negative feedback. Now let us derive the transfer function for a closed loop system in case of a negative feedback. So now we will derive the transfer function of a closed loop system with negative feedback. We are having a closed loop system in which the reference input is Rs. The gain of this system is Gs, and since it is in the forward path of the system, we call this as the forward path gain. Similarly, Hs is the feedback path gain because it occurs in the feedback path of the system, and Cs is the controlled output. Us is the actuating signal. And in case of a unity feedback system, we call this signal as the error signal. And in case of a unity feedback system, the value of feedback path gain Hs is equal to 1. Bs is the feedback signal. If we observe in this feedback path, Bs is the output signal of this feedback path gain, and Cs is the input to this feedback path gain. So we can say that Bs is the product of Hs and Cs. Now if we observe this junction is called as the summing point that we use to add feedback signal with the input signal. So if we observe this summing point, we can write Us equal to Rs minus Bs. Due to negative feedback, the feedback signal Bs is subtracted from the reference signal Rs, and that's why the output to this summing point Us is equal to Rs minus Bs. And we know Bs is the product of Hs and Cs, that's why we can write Rs minus Cs multiplied with Hs. We have replaced Bs with Cs multiplied with Hs. Now if we observe the forward path of the system, then we can say Cs is the multiplication of Gs and the input Us. Us is the input to this system, and that's why Us multiplied with Gs will be equal to Cs. So we can write Cs equal to Us multiplied with Gs. Now we will replace Us with this equation. So we will have Cs equal to Rs minus Bs multiplied with Gs. And Bs is equal to Cs multiplied with Hs. So we will have Cs equal to Rs minus Cs multiplied with Hs multiplied with Gs. So if I repeat this again, if we observe this junction, then Us is equal to Rs minus Bs, Us equal to Rs minus Bs, and if we observe this forward path, then Cs is the multiplication of Gs and the input Us. So Cs equal to Us multiplied with Gs. We have replaced Us with Rs minus Bs, and Bs is the product of Hs and Cs. So we have replaced Bs with Cs Hs. Now we will open this bracket and multiply Gs. So we will have Cs equal to Rs multiplied with Gs, RSGS minus CSHSGS. Now, if we transpose this factor to the left hand side and take CS common, then we will have CS multiplied with 1 plus GSHS equal to RS multiplied with GS. Now RS is the input to the system and CS is the output of the system. So if I transpose RS to the left hand side and if I transpose this factor to the right hand side, then we will have CS over RS, which is the transfer function, equal to GS divided by 1 plus GS multiplied with HS. And this is the transfer function for this closed loop system with negative feedback. If we consider positive feedback, then in that case the transfer function will be CS over RS equal to GS divided by 1 minus GS multiplied with HS. So in place of plus, there will be minus in case of positive feedback. Take this as homework. Derive the transfer function of a closed loop system with positive feedback. So now we have calculated the transfer function of a closed loop system and we know it is equal to GS divided by 1 plus or minus GS multiplied with HS. Positive sign is there in case of negative feedback and negative sign is there in case of positive feedback. Now if we observe, in case of closed loop system, it is forming a closed loop. And that's why this transfer function is called as closed loop transfer function, CLTF. So now we are done calculating the transfer function of a closed loop system and we also know that why this transfer function is called as the closed loop transfer function. So now we will understand the concept of open loop transfer function, OLTF. There is a misconception regarding OLTF that it is a transfer function of an open loop system. But it is not correct. The open loop transfer function is also the characteristic of a closed loop system, like the closed loop transfer function. In case of an open loop transfer function, we do not consider the effect of feedback in the input junction. That means the feedback is present because it is a closed loop system, but we are not adding the feedback signal in the input junction. And that's why now the transfer function will be the product of individual loop gains, which is equal to GS multiplied with HS. So the open loop transfer function is equal to GS multiplied with HS. And since it is not forming a closed loop, it is called as open loop transfer function. But it is a characteristic of a closed loop system. So if we define closed loop transfer function, then it is equal to CS over RS, which is equal to GS divided by 1 plus or minus GS multiplied with HS. And now we know that open loop transfer function is the product of GS and HS. So this GSHS in the denominator of closed loop transfer function is the open loop transfer function. So we can write closed loop transfer function equal to GS divided by 1 plus or minus open loop transfer function. So we can use this formula for calculating the open loop transfer function whenever we have the closed loop transfer function and vice versa. So now we are done with the transfer function of a closed loop system. We have also discussed the closed loop transfer function and the open loop transfer function, and now we will discuss the applications of closed loop transfer function and the open loop transfer function. So we use the closed loop transfer function to analyze the stability of the system by using the RH criteria, whereas we use the open loop transfer function to analyze the steady state errors, to draw the root locus, to draw the Bode plot, and to draw the Nyquist plot. So we can say that the open loop transfer function is used for all purposes except to analyze the stability by using the RH criteria. So now we are done with the applications of closed loop transfer function and the open loop transfer function. We will discuss these things in detail in their respective chapters. Thank you for watching this lecture. I'll end this lecture here. See you in the next one.